right, well, I'm Script Junkie, and this is Ambush. So I'll start off talk a little bit about who I am, talk about why I'm doing this talk, what the motivation is, and what I developed here for this. So if you run into me, it's probably because a lot of development that I did for Metasploit developer, written a bunch of client-side exploits, privilege escalation exploits, a whole bunch of back-end features like interpreter features, webcam stuff, wrote the GUI and a lot of the RPC back-end for that. Also released a number of different attack techniques. I tend to publish things on scriptjunkie.us, so if you want to find me, that's my website, or scriptjunkie1 on Twitter. And day job, I've done a lot of malware reverse engineering, but still, generally speaking, from previous talks that I've given or other stuff that I've released has been basically exclusively offensive. So I did attacks against Office, attacks against Microsoft, attacks against, even turned around did attacks against Metasploit itself. And I was thinking about, well, you know, why am I doing all this attacks? And so I just started thinking about the different perceptions that there are between offense and defense. And generally speaking, on the, you know, offense is more exciting. You know, everyone knows attacking things, blowing things up is more exciting than trying to secure things. If you've got two talks and one of them is, you know, we're going to secure mobile devices, and the other talk is we're going to blow up the iPhone with an exploit, you know, let's be honest, which one are you guys going to go to? We're going to go to the second one because it's awesome. And you know, there are a few other perceptions related to that. A lot of times people say, well, you know, as an attacker, you know, you try something, maybe it doesn't work. You try something, maybe it doesn't work. You try something, and then you get in, and you win, and it's awesome. And as a defender, you try to secure stuff, and everything seems to be going okay, everything seems to be okay, until someone hacks in, and then you lose, and everybody, you know, what happened? You screwed up, all this stuff. So attackers, something happens, and they're winning, they're awesome. Defenders, something happens, and they're losing. It's painful. And, you know, another frustration that I've heard a lot is that attackers, they get to solve technical problems. They get to figure out how to break into places, find holes in security. But, you know, defenders, well, they just pretty much fight organizational bureaucracy as they're trying to fix their stuff. And so I can't help you with a lot of these, but one of the perceptions that I've heard time and time again is this idea that I'm calling the myth. It's the idea that well, defense is tough because attackers only have to win once. And, you know, I heard this and I was thinking, you know, this really shouldn't be the case. Or maybe it is the case, but it shouldn't be. And the reason that is because defenders, that's coming from an idea of defense that I'm calling the wall. And so the wall is pretty simple. You've got your simple little diagram here. I took an example of the JDK 1.0 security model. This is actually a diagram that they put in the documentation here. So you've got your little box here, and inside this little box, the attackers can do whatever they want. They got this sandbox. They can go display stuff on their little corner of the applet. They can display pictures, do memory stuff, but they can't go down here and touch any of your files. They can't read the registry. They can't write stuff. All that's outside the sandbox. So we got this hard wall, and it doesn't matter. They can, you know, they obviously have access to Java. They can look at that, but even though they know everything which is out there, they still can't get from the inside to the outside, kind of the Kirchhoff principle. And of course, this is a great idea, but of course, what happens? Well, then you have attacks against that. So, you know, every month, you know, comes along Patch Tuesday and a Java 0 day, and people come with exploits all the time for this kind of stuff. And even if they don't, you still have, you know, the signed applets that people can put up. And a lot of pen testers I talk to, I use them all the time. You just hand somebody a sign applet, everybody, you know, half the people are going to click through and just give you access anyway. So you've got attacks where either you just break through the barrier or you get around it, you trick somebody into running authorized code, and it is it is very difficult. As a defender, if you go ahead and you set up your network so you're relying on this, you're going to fail again and again. And so on the defense, well, what can you do? You can basically brush your teeth and floss and look both ways before you cross the street. Or in other words, you patch your systems and you train the monkeys not to click the buttons, and it doesn't work because some of them do anyway. And people come out with attacks, and you have boxes on your network that you don't even know where they came from, but they get owned, and people plug in thumb drives, and it's not a way in itself of maintaining security. And so I started thinking, well, I still feel like I'm a relative newcomer to the security area because I've only been contributing stuff for a few years. But I'm doing, when I start out, you look at hacking, it looks like magic. It's all this amazing, you're doing something where nobody even knows what's happening. When you come up with an exploit for a software, you feel smarter than everybody who designed that software and everybody who developed that software. But after a while, I realized really the more amazing thing was doing defense. I feel like it's more, if you can put up a successful defense, that's really honestly harder once I began to learn and really discover all the different ways of attacking. And so that's what I want to talk about contributing here. So we talked about our basic defense. Of course, that's going to fail, and everybody knows that. So what can you do instead? Well, what you want to do is you want to basically flip the system on the head of the attacker and set up a lot of points of defense. And so, well, what do I mean by this? Well, for example, you have a lot of external points of defense. So let's say we're going from the perspective of a criminal who's trying to own a bunch of clients, set up a botnet, steal your credit cards, cash out, and make money. Basically, any number of the standard cyber criminal tactics. Well, first, I've got to go ahead and set up domains, and I've got to set up some type of black hat SEO or advertising, or somehow I got to get traffic to these domains, and I've got to get exploits, like buy an exploit pack or something, set it up here, and I've got to do all this to get traffic to the domain. And at any point along this route, while I'm buying domains, there's innumerable ways that credit card transaction, whatever, that could get traced back to me, and I could potentially be caught. If I'm going out there setting up servers, somehow I've got to get a server to host my malicious content, and whether I go out and buy that or I try to hack somebody else's server, all of those are things where it's very easy for me to make a mistake and get caught. And once I've done all that, I've got to go ahead and create malicious code, create my backdoor, modify it, or buy it from somebody that will bypass all the antiviruses. And that might work for a while until they get a sample, and then maybe they push out a signature, and then I got to do a lot more work to maintain that. And even after the whole infection cycle and cycle of stealing credit cards, getting passwords, hacking into sites, let's say I go ahead and do that and get all your credit cards, and I've stolen all your bank account numbers. Now I've got to cash that out. And once again, there's an opportunity for me to get caught. And that is how, honestly, a lot of the cyber criminals get caught. That's why, even though so many systems are vulnerable, although a lot of malware does tend to end up on them, if you look at the potential between number of people who are getting their credit cards stolen on a daily basis and number of people who theoretically could, it's a lot smaller. So there are lots of external defenses out there. Let's say I even bypass all those, then I have to hit network defenses. So if I'm in charge of a big network, I can set up all kinds of perimeter intrusion detection systems. I can set up firewalls, whitelists, all kinds of different defenses at the network. And that's going to stop a lot of attacks. If you get through those, then of course there's host attacks. I can install antivirus, which is everybody's favorite. Although, yes, it doesn't do a whole lot for prevention because it's not too difficult to bypass. It's actually great for cleanup. Although it's not going to catch, for example, Flame. You look at some of the high-profile malwares. As soon as antivirus companies recognized a sample of that, it was gone from tens of thousands of systems. So antivirus does definitely pose a big issue to the entire attack life cycle, even though it's not necessarily difficult to bypass in the first place. And then you have host intrusion prevention systems. So I can write rules to prevent common malware, drop locations, and persistence techniques, and that's all different things that I can do at the host level. I could also install Emmet or something like that to try to block exploits. And of course, we talked about antivirus. And what's the issue with this? The issue with this is what I'm calling the one-size-fits-all defense. And that is, if you look back at, for example, the Flame or the other pieces of malware, I can, as an attacker, put together an attack. I can get access to all the tools that you are likely to have. So I can get access to your antivirus. I can get access to your host intrusion prevention system. I can access to different pieces of network equipment. I know basically what an IDS can see, and I can do a whole lot of obfuscation to bypass that. And though I can do that, your basic defense is to rely on more behavior-based defenses. And so that's, for example, the host intrusion prevention systems that we talked about. But even so, the HIPs that are out there tend to be very restricted. So this is what I'm calling the main problem. When attackers go ahead and load up this, they can get access to a sample of your antivirus and your HIPs. And what they're going to find is that it only watches a number of set points. So for example, most HIPs out there will watch file access, and they'll watch registry access. And you can write a rule for these particular files can be touched, these particular registry values can be touched. But at most, there's going to be about 10 points that they're going to watch. And with that, I know that these are going to be watching these particular points, or going to be watching network traffic. And since I know that network traffic is very likely going to be watched, what I can do is put a ton of obfuscation on that, put a ton of encryption on that, and make sure that it would be very difficult for any signature to catch that traffic. When we're talking about, these are my slides. When we're talking about the, there, that broke. When we're talking about the user mode hooks, a lot of host intrusion prevention systems are based on hooks that are made in user mode. So basically, I'm going to hook this particular function. So for example, McAfee, Komodo, Sophos, all rely on user mode hooks internally. And if I know where those are, I know you're going to watch this particular, say, process injection function, open process. I can then either try to skip the hook, which is going to redirect the first few bytes of the function, or I can call a lower layer functions and emulate the functionality, or I can even skip those entirely and jump straight to the kernel by making direct syscalls. And that is definitely a big problem, because since I know where the points are ahead of time that you're going to be watching, it is not too difficult for me to bypass them. It takes some amount of effort, but it's not too difficult. And this is basically the types of things that we're seeing out there. So for example, you look at Gauss, Flame, a lot of them were written in such a way where they know that certain points weren't being watched. So for example, the .ocx files were not being watched by McAfee. So they were able to create generic bypasses for most antiviruses because they knew which points were being watched. And so once you know that, well then, you become basically like the invisible guy in crisis, and the antivirus or host intrusion prevention systems which you are defending against won't stop you. So I'm putting together basically a new approach. And this is why I wrote Ambush. Ambush is a host intrusion prevention system that I wrote to get over this by having a lot of basically unlimited possibilities for detecting and stopping malicious code. So basically, rather than the individual point defense, have a lot of overlapping areas of security and have those at any particular point so that you can't know ahead of time where that's going to be. And the reason that is because evading point checks is hard. If you look at, for example, Dooku, another one of the famous high-profile pieces of malware out there attributed to nation states, it used an unusual technique for process injection. So prior to Dooku, there's different techniques for getting a handle to an open process, whether creating or opening a process. There's different techniques for getting memory in the process, so you can allocate new memory or you can override existing code. Then process injection methods would call write process memory to get your code over there. And then there's different techniques for starting that code. So you could hijack an existing thread or create a new thread was more common. But all the different process injection methods used that write process memory or the syscall equivalent of it. Well, Dooku used a different technique. They used a map view of section, which is normally only used when you're creating a new process. And so this new technique meant that they bypassed all the host intrusion prevention systems that were watching that point of writing memory into a remote process. But that's hard. It's very difficult to find those new techniques. However, once they did that, it was worth it because creating point checks is hard. And one of the, another example that we go to is this. I saw this on a forum the other day. I thought it was a perfect example of what I was trying to get across. Here, somebody installed a host intrusion prevention system called Dynamic Security Agent. Ran a bunch of tests that caught some keyloggers, but it didn't catch one that was called Martin's undetectable keylogger. And the reason that was because it was monitoring common keylogger functions such as set Windows hook or get async key state, but Martin's undetectable keylogger came out with a way to do it with a different function, get key state called rapidly and monitoring keyboard buffer via that technique. And so once the keylogger, Martin or whoever invented that keylogger, came up with that technique, he was then home free from host intrusion prevention systems like DSA. And the reason that was because there wasn't any easy way that they could adjust to that. So for example, the question was asked, okay, well, how do I detect this? And the answer was, well, you could wait a couple of years, maybe they'll release an upgraded version that will have a detection for this technique, or maybe you could get an entirely different host intrusion prevention system, but that might have its own gaps. But there's really nothing that you can do to compensate for that. Well, not anymore. That's the idea behind Ambush, is that now we can take a host intrusion prevention system, and the idea behind Ambush is that you can create a signature for any function of any exported function of any DLL system-wide, and you can write a signature for it, defining what the parameters to that function are, different restrictions on return address or caller or calling process, and now basically you're not limited in terms of what you can monitor and what you can't. So if you're not super familiar with programming in terms of Windows, that's fine. Anytime that your program wants to interact with the hardware, send packets out, write files, write registry entries, mess with another process, keylog, VNC, anything that a bad guy or a good guy might want to do with the system, it has to go out and call API functions. And so these are functions exported in DLLs, which Windows provides, and there are thousands, if not tens of thousands of them around, and they basically control how everything is done. So Windows provides these system libraries. Now, in contrast with Linux, where many programs are compiled to directly call to the kernel, on Windows, DLLs generally have to be used in order to make your programs work cross-platform, because every different Windows version has a different set of syscalls, and if you try to directly call to the kernel, that won't work because you'll end up breaking things across different service pack versions or different Windows versions. So I targeted the API functions that were made, and I also wanted to target Ambush at some of the higher layer API functions. So sometimes you're looking at malicious activity, and you find that shellcode, for example, used in a lot of exploits, often uses URL download to file. That's one function which Windows provides, which is a very high layer function, which handles the entire connect to a remote system, download a file, save it to your disk. That's very handy for them to download an executable, a piece of malware, and then run it. They can just call this one function and then call another function to run it, the function winexec. But what's interesting is this function, URL download file, is not used by Internet Explorer, it's not used by Firefox, not used by any of your browsers, because they all want to have control over the download speed, they want to show you progress, they want to give you the choice of where to save it, they want to cache it, they want to send cookies, and all those other interesting pieces of activity. So this function is extremely rare with legitimate software, and that is extremely common with malicious attacks. So it's a perfect opportunity. You could write a signature that says if this function is called, you could block it entirely, or you could send an alert if this function is called. And you're, generally speaking, going to catch all this malicious activity, but not the good activity. So the question is, if you're interested in technical details of how you accomplish a signature system that will work on any export DLL and any number of export DLLs, it's by an expanded view of dynamic hooking. So if we open that up, I have to rely on a lot of dynamic code generation because I can't know ahead of time, obviously, what I'm hooking or where to put signatures on. So this is basically what's going to happen. You're going to have, your program's going to make a call to an API function, to the start of the API function. Normally that would continue through the body of the function and return back to the program. What I do is I overwrite the first few bytes of the function with a jump to a piece of dynamically generated executable code, a few instructions, which will then, each one, I have to use this springboard, a different springboard for every function that I hook. And the springboard has to pull up a pointer to the configuration which defines what to do with that function, so that when it jumps to my hook function here, which evaluates the called function and arguments and decides whether or not I'm going to block this or I'm going to allow this. So it knows which function is being called, because this logic ends up getting called for all functions that I write signatures for that I hook. So once it jumps through the springboard, it hits this, and that evaluates the signature and says, is this a function I want to block? Is this a function I want to allow? Do I send an alert but let it go? And it handles that before the call is actually made, so I could block it and prevent from happening. Then I want to jump back to the call, so I got to reconstruct the arguments that are on the stack. I have another piece of dynamically generated code to do that, and then jump to the real API function. So that goes, executes whatever, sends a syscall to the kernel saying write this file, or whatever your API call is doing, and then that returns. And that goes back up to my hook function over here, which then evaluates post-call actions. So you can also write actions that run after the call. So for example, I could say, if you call receive, if you receive data from the network, and that you end up receiving these bytes, then kill the process or throw an alert. So this is also a possibility. At that point, let's say we say, no, we're going to let it go. Then we will go ahead and clean up the stack and return to the program, which is, again, dynamically generated, so that I know which one to jump to. So once I have this dynamic hooking, I can now go ahead and write these signatures for anything. Now, there are a couple of really interesting technical challenges that I ran into when I was writing this up. So first of all, you have the different calling conventions which are out there. Now, Windows uses a convention called the standard API calling convention. That means that when you're calling a function, you push pointers to your arguments or your arguments onto the stack, and then you jump to that function. And that function then executes, looks at the arguments up there, and then returns and cleans up the stack for you. There are some good parts to that and some bad parts. First of all, the way the arguments are pushed down, I could simply get a pointer to the first argument by looking at the stack and then index all arguments based on that. So if my signature says there are 5 arguments, I could just treat them as an array of 5 arguments, which was very helpful. But on the other end, returning back was a little more difficult because I needed to dynamically generate code. I needed to figure out how many arguments. I needed to know how many arguments ahead of time are there before I can return to that. Now there's another calling convention which shows up occasionally and shows up more commonly in external libraries called the cDecl calling convention. The C calling convention, the caller pushes the arguments onto the stack and then cleans the arguments back off the stack. So you have to use this function if you have a function like printf, which takes a variable number of arguments. The problem with a function like that is I don't know ahead of time how many arguments there are. And because of how I had done the function hooking, at this point I'm not supporting cDecl calling convention because it would require a rewrite of how I did the 32-bit hooks. Now on 64-bit they've got an entirely different system, which is fast call basically, which means some of the arguments are in registers and some of the arguments are on the stack, but you don't necessarily know. So I had to write some code to make sure that what I do is I take the called arguments, push them all onto the stack to make sure that they are all in line, and then go jump to the logic which parses those out. Another issue that I ran into was the dynamic loads. So how to get ambush loaded into every process, which I did through a combination of appendant DLLs and hook and create process calls. So when you create a new process, it will inject ambush into the new process. As that happens, so it will be loaded into all following processes. And then I also, once it gets loaded up, then I'll look and see what DLLs are loaded and see if I have any signatures for those. But I also need to watch out because DLLs could be loaded at any time. And so I also hook the loader load DLL, the internal DLL loading function in NTDLL, so that I can catch those and hook those if I have signatures for those as well. I did run into a number of interesting assembly complexities when we were trying to do this hook. So many Windows API functions, such as most of the kernel 32, the ones that are exposed and designed to be intended for end users to call, have something called hot patch points. So they've given you a few bytes that at the beginning of the function that don't do anything, which you can overwrite with your jump safely and very easily to accomplish a hook. However, the internal function calls and a lot of the more interesting functions don't have this because they aren't intended for all you end developers to call, and so they don't have that. That meant that I had to include a disassembler in my code, which will parse out what instructions there are so that I can find out how to reconstruct them on the other end and call them. Sometimes it was interesting because it wasn't simply just instructions, they actually included jumps as well, or comparisons, basically branches, if statements. And so sometimes the first few bytes of the function would have an if this, go here, else go there. I still wanted to be able to hook these functions, so what I ended up doing was reading in those instructions, recreating those, and changing the jump so that there were two possible exit points from my hook. So it'll do the comparison and jump to another dynamically generated jump, which will then jump to wherever the location was of that branch. So it maintains the integrity of the branches as well. However, there is a possibility when you're doing this overriding first few instructions of a function that there will be some kind of a loop that will jump back into the middle of the first few bytes, and since I've overwritten those, the instructions might not line up and you could cause a crash. So it's rare, but some functions you could end up breaking simply because we're doing this on any number of functions and we're not knowing ahead of time what we're hooking. So there is a possibility that that could happen. Another interesting thing was when Windows 8 came around, I got the developer preview and the consumer release preview. They changed a lot of things internally. They changed how the hot patch points look. They changed how DLLs are loaded. They introduced a weird DLL loading mechanism. That seems to happen with every Windows version. And a bunch of other issues I ran into with Windows 8. So if you are using this on Windows 8, I don't know if there are still any serious issues, but you could run into a couple there. So having all this, all right, we can now intercept any function out there. We can now write signatures for it. What's the bad news? Well, the first issue with this, and probably the biggest issue, is simply the operational challenge of being able to understand the level of detail necessary to write these signatures and to do it correctly. So I've got good reason to believe that internally the people at McAfee and elsewhere can actually write signatures with this level of fidelity, but they've never given their customers, host intrusion prevention system customers, the ability to do this. And the reason that is because it's very easy to write a signature when you're doing this, any API call system-wide that will simply brick your system. So if you block a call or kill a process and that ends up being used internally by service host or WinLogon, some core Windows process, that will very easily end up breaking your system so that you won't be able to even boot. So you do have to watch about that. The other issue is just simply the knowledge that you need to understand shellcode at a level of detail or malicious code at a level of detail to perform this. You might be thinking, well, I don't know if I want to touch this because I can't do that. But honestly, there are a lot of large companies out there which do have malware analysts. And there are most companies out there, although they don't have large security teams, they'll hire companies to go set up their security. You're already hiring companies to go do pen tests. And there's definitely an opportunity for security experts to come in, set this up, and get it ready to go. So I think that Ambush is basically, I designed it to put the biggest machine gun in your hands that you can find. It's a bigger gun than you can find anywhere else, and you can totally shoot your foot off with it. But it also gives you a lot of power that you haven't had before in order to combat malware. And it allows you to do things like, for example, stop whole methods of execution, such as the URL download a file. So McAfee can't write a signature that will block that, because even though it's extremely rare with legitimate software, there is some legitimate software that uses it. So it's very difficult for any of the companies out there to block whole classes of malicious behavior. But you could do that if you don't use that in your network or on your systems. And so you can get a lot more powerful with this. But the bigger challenge, the bigger bad news is the fact that if someone is running executable code on your system, whether through a exploit shellcode or whether through malicious logic, they've got a piece of malware on your system, they can bypass user mode hooks. There's nothing stopping them. There's no privilege barrier that's preventing them from making direct syscalls or possibly trying to bypass your hook, although it will be more difficult because they won't know where that is. They can still do that. And so the way to get around that, which has always been used in the past, for example, there's an academic HIPS called WIPS, Windows HIPS, that would do kernel hooking. Basically, it would hook these syscalls into the kernel and monitor those so that there wasn't any good way that you could use of bypassing it. The problem with that is, with the introduction of Windows 64-bit, now you have to have all your Windows drivers signed, and because of patch guard, kernel patch protection, they're not going to let you touch the structures. Big asterisk at the end of that for all our exploit developers in the audience. Yes, I know there are bypasses out there. They come out with bypasses like about every year. But if I'm going to write a host intrusion prevention system, which everybody's going to use, it would be a really bad idea to rely on that, because that could easily backfire. As soon as Microsoft finds a bypass, they usually change their code to make it so you can't. Then that bypass will break, and anybody who has that software running, their system will blue screen. And then by disabling patch guard, people could argue that you're disabling a good security feature against rootkits, et cetera. So I don't want to go that route, which basically means at this time, I'm stuck in user mode. And that means that bypasses are possible. So what I want to do was, putting back on my attack hat, because let's be honest, I like doing that, I thought, well, what can I do to bypass this? So I know I'm not the only one using these techniques. Like I said, Komodo uses them, McAfee HIPS uses them, Sophos HIPS uses them, I believe Symantec also uses them. Almost every security product out there that you can find uses these kinds of hooks. So I put together something called Hoarder. And the idea behind Hoarder is, okay, that's not particularly, all right. The idea behind Hoarder is to create a piece of malware that will incorporate all the functionality that's necessary for running within the piece of malware itself. So syscall bypasses are normally very difficult and probably not practical for shellcode because you have to basically recreate the functionality of all those Windows DLLs, which is a lot of code. So what I did was I created a tool that maybe I can't fix that aspect, but if I've gotten past the initial infection point, I can create an executable which has all of that functionality built in. So what I'm going to do is I'm basically going to take an executable, find all the DLLs which it loads, pull those into basically byte arrays within my own executable, manually load those or map those into memory, hook up all the imports, and then without calling any of the real DLLs, I'm working on bit-for-bit copies that I've loaded into memory. So if you're hooking all the real functions, you're not going to see anything, but I can go ahead and do this from memory. So let's see how this works. Start out with, this is the program which we're going to make statically compiled effectively. We're going to assimilate all the DLLs into. So this is basically the Windows API hello world. All I do is use Windows API functions to get standard output handle and then write hello world to it, 12 bytes. I don't care about the return value for that. So I can go ahead and create this. So I go ahead, close that. Boom. Hey, I'm not running Windows. So we run that, and sure enough, get a hello world out. Simple, nothing to it. I wrote it in this way rather than using a C runtime library, did some compiler options so that it wouldn't pull in a ton of library code. So all it has is these functions which I'm executing. This is the entirety of the assembly of the executable. Basically, we just call get standard handle, then we call write file. As you can see, these two are imported, from kernel 32. So let's say this is my evil executable, which is going to trigger the nuclear bomb and destroy the world by writing hello world to standard output. And so my arch nemesis has discovered that I have this evil executable here to launch hello world and destroy the world. And so they've written signatures for this. And so I don't want to have any of my functions get caught by these signatures, so I want to statically compile that. So the first thing I need to do is identify all the DLLs which are loaded by this. And like I said, this is going to have to be very specific to your operating system architecture and service pack because the syscalls are going to change, the DLLs are going to change regardless. So I'm going to call get DLLs on hello world.exe. This is a tool that I wrote which is going to load up hello world.exe. It's going to go through the import table and say, oh, it imports kernel32.dll. It's then going to load up kernel32.dll and take the bytes of that, put it into a C source file so that I can use in my assimilated hoarder project. It's then going to find imports to kernel32.dll. It's going to run to a lot of these, API, MS, WinCore, blah, blah, blah.dll. This is a weird, stupid DLL loading thing which Microsoft added in Windows 7. These DLLs don't actually exist. Actually, they do, but they aren't actually loaded and they don't actually do anything. They're actually alias to kernel32.dll or ntdll. And so short story is it's going to find all the DLLs, find all the numerous aliases to the DLLs that are loaded, and put that all together in C source code so that I can copy and paste this into my hoarder project. So hoarder is going to hoard all of its DLLs, and this is basically the code to that. So once I have all these images of the DLLs in memory, so I've got the original bits all as part of my executable. Then all I need is one syscall, which is ntallocate virtual memory to get memory to map these into memory. And then I can use the reflective loader from Metasploit to load the DLLs in memory without actually touching disk, opening a file, calling any Windows API functions. And once I've done that, hook them all up, and I will have an executable which does not import any Windows API functions. So first of all, I'm going to call, that's not the right path. So I'm going to go ahead and call hoarder, and sure enough, it's going to print out hello world. So went ahead and did that. Let's see what hoarder looks like under IDA. Oh look, there are no imports. What's interesting is not only do I not import any functions, I don't even find any DLLs in memory and call them. I operate entirely within my own executable. So that's pretty cool. Here's, as you can see, we've got a whole lot of, here's all the code for how it sets itself up internally. And instead of our simple flowchart, we've got this massive bunch of function calls. So I suppose this could also aid in frustrating reverse engineers who not only have your code in the executable, they now have all of the Windows API code in your executable. And it'll be a pain in the neck because they'll have to find every one of these is a different function. So I guess that's a side benefit. It is, well, it entirely depends on how many DLLs that you have loaded. So this one, because I'm only using kernel 32, used kernel 32, kernel base, and NTDLL. So this one was only a few megabytes, but it can go up to about 10 megabytes, 15, 20 megabytes. So that's fun. Let's close this out. You might be thinking, well, that's great. You just wrote a bypass for the tool that you're trying to hawk. That's kind of stupid. Why'd you do that? Jeez. Well, and the answer is, let me pull this back up. Close this out. And come back up. All right. So the answer to that is because although nobody's gotten to that point, I haven't seen that done in the wild yet. People have done HIPS bypasses. And I still want to say that I basically want to do that to spike any of the arguments that I know are going to come out later, which is this is too difficult. And basically show you that this does still matter. And the reason that this still matters is because, first of all, that hoarder, the reason I did it with direct syscalls, it didn't even pull up any library code, is that the library code uses a lot of, basically any functionality which depends on those DLLs actually mapping to actual file handles, or those DLLs matching what is in the process environment block, basically structures which Windows has in the process telling you which DLLs are loaded. Anything that relies on any of those data structures being accurate will actually crash if you use hoarder. So that is almost any significant piece of code will actually crash. That technique will be far more difficult and won't actually work for real software. The other issue is that this won't work for shellcode, like I said, and there's a lot of instances in which this can't be bypassed. So, for example, most of the exploits that we're seeing out there in the wild, especially some of the top of the line exploits which everybody is using, are not in fact even memory corruption exploits anymore. So you take a look at, for example, Stuxnet used 4 0 days. 3 of those 0 days were non-memory corruption exploits. And so what I mean by that is they took advantage of a logic flaw to have the print spooler write a file to somewhere it shouldn't. Well, I can write a signature hooking that and saying don't do that. Since they're not making that direct syscall themselves, but they're relying on somebody else to do that, they can't bypass that hook. When you're doing almost all of the Java 0 days, which have been dropped that everybody's been using, they will rely on Java functionality for writing a file or executing a process. Well, when Java executes that, you can't just say skip these bytes of this function and jump here, because you're running interpreted code. You look at all the command injection bugs. One of the only publicly released exploits for Google Chrome was a command injection bug. That type of functionality, once again, you're not executing direct bytes where you can say skip this and make this syscall. You're relying on that all going through the normal execution chain. So in almost all cases, the initial infection is not going to be able to bypass signatures like this. The other interesting thing is the fact that the bypasses generally tend to be very difficult. It's interesting. I would expect out there to see more malware doing these bypasses, but what's interesting is there's actually a presentation at Black Hat this year, a scientific study of over 4 million pieces of live malware samples. They found only a fraction of 1% actually performed any hook bypass. So for whatever reason, although anti-debugging shows up all the time, although anti-VM shows up all the time, even though hooks have been used by reverse engineers forever and ever, malware authors, there is evidence to show that malware authors do consider that to be more difficult than some of the other anti-reversing techniques that they employ. And finally, I just want to talk a little bit about different strategies. So different strategies have been proposed for securing things. One of them is no bug. Well, you shouldn't use software with bugs. One of them is blame the user. So basically, these are your alternatives. This one I thought was kind of funny. Twitter from Dan Kaminsky says basically, show me that AV actually stops anything. And then Mikko, who's an AV guy, says, yeah, well, we just stopped, almost 500 people from getting infected by something. And then, attrition.org says, well, those 500 people probably shouldn't be allowed to use a computer, right? So that's one strategy we can use. We could blame the user, right? I mean, no telling if they, used an O day on, a site where normal people go. It's just blame the user, right? That works. But if you look at a successful strategy, there's a paper written by the Lockheed guys that I won't go into too much because I'm running out of time here. I really want to do some demos, which talks about multi-layered defense. And if you identify your attackers, monitor every step of the way that they use for their intrusion, you can catch them when they launch another attack if they haven't changed up absolutely everything. And so they had like 7 different points where you could monitor attackers. And it's interesting from that perspective because they're probably the only example that I know of where someone has faced significant adversaries, in this case launching multiple 0 days, has actually stopped them and will actually tell you about how they did it. And so that's basically how they did it. They monitored how they sent out their malware, where it called back to, what the droppers looked like, and they had about 7 different characteristics. Well, with Ambush, you could write easily 100 different characteristics or 1,000 different characteristics of their executables and every API call which is made. And so we mentioned commercial hipses, and let's go do demos. All right, so I have a demo for Metasploit. I've got a live demo for Elnor Exploit Pack, and I've got a live demo for Poison Ivy. So the question to the audience is, who do you fear more? Your auditors, APT, or cyber criminals? We'll do as many as we have option. Shout something out. Cyber criminals. All right, we're going to do an exploit demo. So this one's interesting because it relies on me actually getting out to the internet. So we'll cross our fingers and deny the existence of the demo gods and hope that this runs. All right, so I'm going to start out with this. Hopefully this will work. This is the Elnor exploit pack that I have set up on my domain, techtest.com. I got nothing up here, and start up my VM. So Ambush, I wrote to support Windows Vista and 7 because I didn't want to deal with some of the older XP stuff. So I'm not going to guarantee it supports it on the earlier. I've heard it doesn't work on XP 64-bit because honestly, if you're using XP, you have other security issues. But I couldn't get the Elnor exploit pack to work reliably on any of the higher versions, so I went ahead and installed this. So what I'm going to do is I'm going to go ahead and update my signatures. I'm going to go ahead and open up my Ambush. So I've got a few signatures set up here in the demo set, and basically to create one of these signatures, I'm going to use, so for example, we talked about URL downloaded file. So this is a signature. To create it, I just put in a name, put in what I want to do, severity. I can put in notes if I want. I can do a black or white list for a processor calling module. I select which function I want to call, and then put in the arguments here. That one didn't end up in my functionality, but here's one that will come up. And so you have, it'll pull up the definition if it has it automatically for you. If not, you can enter it manually. I had to enter it manually for your old downloaded file. So I got these signatures set up, and I have almost all of them set to alert except for URL downloaded file, which is set to block. All right, so I'm going to open up my browser, go to the exploit pack, wait a second. I love how the authors just put like a little da-da-da-da-da, whatever here. And so it's going to detect my browser, detect my service pack, go redirect me to a page which is going to serve me a bunch of exploits. And nothing's going to happen, which is exactly what should happen. Boom! This is what happened. So we had, we have a couple false positives here. I put write process memory because it's very common, like I said, for process injection. There's a couple instances where that will actually happen. And then what's all this? So we had a couple of calls here from outside any mapped module. Basically, the shell code got executed, called URL download to file A. Oh look, tried to download this particular file and save it as e.exe. This was blocked. Then the shellcode tried to call winexec on that particular exe. So that entire exploit path we have just created and stopped with ambush. Well, let's see how it works with Metasploit just to fire that up. So here's, let me pull up the, while this is loading, I can go ahead and pull up the Eleanor shellcode. So Eleanor has a bit of shellcode to go ahead and resolve imports and call them, and then you get to this piece of shellcode, which is the interesting part, which actually calls get temp path. You can see it calls the load library for URL mon.dll, and then it calls URL download to file A of temp.exe, and then winexec. So these are the functions right here, which we saw, which we caught, and which we blocked. What's interesting is Metasploit has a similar functionality. Here's the Metasploit reverse TCP handler. So any reverse TCP, whether that's an interpreter or whatever, is going to go on this. It's going to call load library for winsock32.dll, then call a bunch of functions to connect back and load the executable. So what I've done is write a signature to catch that. So let's go ahead and pull in our updated code. And then, all right, we got our alerts up. Let's clear this just so that we can see our new alerts. So what we're going to do is we're going to open up. So first of all, I'll show you opening up a good PDF. All is normal. Yay, neato. And everything works fine. I open up this PDF that Script Junkie sent me in an email, and oh, what's this? I get a shell. So I get an interpreter session. That's very interesting. If I wait about 20 seconds for the alerts to cache and send up, then they'll show up over here. And at this point, for these signatures, I sent them all to alert just so you could watch how many times it gets caught. So sure enough, boom, here we go. From outside any map module, we see load library WS232. So here's our initial shellcode. Here's all the other functions that we blocked, and as you can see, it loads up additional functionality, all within the interpreter payload. So if I go migrate, let's say we migrate to a new process, that'll also show up. So we've gone ahead and caught up all these. With that, that's pretty much my presentation. I'd love to see ambush used. It's set up in such a way where I'd love to see it pushed out everywhere. So if anybody's interested, definitely shoot me a line and come and ask me if you have any questions. Then that will be it. Thanks. Thanks. If you're interested here, you can